Hello, my name is Natalia Molchanova. I'm a third-year PhD student at the University of Lausanne, working on explainable AI for multiple sclerosis patient support. This video is a part of uncertainty quantification tutorial held at MICCAI 2024 conference. This video includes a hands-on session that was not presented during the satellite event. Within the tutorial, we discussed several uncertainty quantification methods popular in medical image analysis. These include deep ensemble, Monte Carlo dropout, test time augmentations, among many others. The most popular method in medical image analysis is Monte Carlo dropout. Thus, today we will look into how Monte Carlo dropout can be applied into a simple medical image classification task. We'll look both into the theory and into the practical implementation using a PyTorch and Monte libraries. Let me first start with how the Monte Carlo dropout method works. Normally, we use dropout in a neural network as a way of regularization. For this, we randomly switch off neurons of a neural network during the training procedure. The Monte Carlo dropout method uses dropout layers during the inference time to compute uncertainty. First, we'll train a neural network architecture with dropout layers used during the training to provide regularization. Going to the inference time, we'll run the inference on this network with dropout turned on for n iterations. Each iteration will correspond to a different subset of neurons that are dropped out. Thus, the final prediction, will be different for each of these dropout masks. Given these outputs, quantifying the spread in the predictions, we'll be able to estimate the uncertainty. The key insight behind the Monte Carlo dropout is that the dropout mask can be seen as a random variable that induces a distribution over the weights and biases of the network. Let's now look at the Monte Carlo dropout method work on practice. To access the hands-on part of the tutorial, please go to the website of the tutorial, and here in the materials you will be able to access our GitHub. The GitHub provides all the materials of the tutorial, including the previous years. Here we're interested in the uncertainty part, and we're looking for this Jupyter notebook. Here you can press the button to open the notebook in the Collab. Collab notebook allows us to use the GPUs, so make sure you use the GPU option here. This hands-on implements a simple uncertainty quantification pipeline that will include a deep learning system that takes as an input an image, and in the end predicts some output for this image as well as the uncertainty score. You can start the notebook execution by running the setup, which will take some time to download the data and all the required libraries. For now, we'll have a look at what kind of task we're using for the tutorial. As mentioned, it's a simple image classification task. So we're using this MedMNIST library that provides state-of-the-art datasets for medical image analysis. And here we're using this dataset with diabetic retinopathy images from fundus camera. So those are small images of the size 28 by 28 and 3 channels. And we'll classify each of this image to one of 5 classes. So the setup was complete, and we can now display these images. In this first cell, we simply define the transforms that will be applied to each of the images, and we also load the data sets, including training, validation, and testing. Here we display the images that we're dealing with. So each of the circles is an image that will classify to one of the 5 classes. Here's a small reminder about the Monte Carlo dropout method work. We have just discussed this. One of the important points mentioned here is that Monte Carlo dropout is a stochastic method, so you will need to fix the random seed. This is an important point for the repeatability purposes if you want to run your algorithm several times and have some repetition of the results. It is worth mentioning that if you're using GPU with a PyTorch, the repeatability is not guaranteed, so there's some degree of stochasticity. So be careful. And within this notebook, what we'll do, we'll train a model with the dropout layers and a fixed dropout probability. We will then run the inference for a test example. We'll generate n samples by derivatively changing the dropout mask. And finally, using the outputs from these n samples, we'll compute the uncertainty by quantifying the spread of the data examples. First, let me introduce you to the architecture that we're using. We're basically adopting a ResNet 18, which is a relatively small model. And in this ResNet, we place a dropout layer just before the final linear layer. Here probably it makes sense to discuss where exactly should we place the dropout layers in our architectures. And I wouldn't say that in medical image analysis there is a straight agreement on that. I would say that researchers experiment with different schemes by placing dropout before some of the layers and leaving others without the dropout, or placing dropout only before the linear layers but not before convolutional layers. So there is no straightforward answer. Ideally, you would need to experiment both with the placement of the dropout layers and with the choice of the dropout probability. So let's initialize our architecture. Here we just plot the architecture so you have a better idea of what we're dealing with and where the dropout layer is placed. So it's just before the last linear layer. This is the function that will define one training epoch. And this cell implements the whole training procedure, and we take only 10 epochs here, which for our purposes of introduction to the topic is sufficient, but of course you need to train your architectures longer. We see the improvement in the classification quality. Architecture has already been trained for 10 epochs, so we can proceed to the inference and get a sense of how to run the Monte Carlo dropout. So first, to run the Monte Carlo dropout, we'll need to decide on the number of samples that we want to generate. And here there is also no straightforward answer. You need to consider the fact that each run will increase the computational cost of whatever algorithm you're developing. I took 10 samples, which in my opinion is quite a generous amount. Then we take some kind of image from the test dataset, and we put the model into the evaluation mode. This said, when we put the model into the evaluation mode, we need to turn on back the dropout layers, because this mode will basically switch them off. This will search all the dropout layers in our architecture, and we will put them into the training mode. So then when we run the inference, the dropout mask will be randomly applied to the layer. And here we'll run the inference n times, which is 10 in our case, and apply the softmax in the end. So Medinist is not defined. I think I just need to delete this part. Yes. So here's just the display of the image that we're trying to classify, and it's a very tiny image. Let's now, given this Monte-Carlo dropout samples vector, look into how we can compute the uncertainty from it. So here is the Monte-Carlo dropout samples tensor. You can see that it has the number of rows equal to the number of Monte-Carlo dropout samples that were generated, and the number of columns equal to the number of classes. Then if we apply the argmax, we can compute the class that was predicted for each of the samples. For example, for this first sample, applying argmax, the class is 0. But for the fourth sample, the argmax tells us that the class is 1, right? Indeed, we see already here there's some disagreement between what class is chosen by the neural network at different dropout masks. The final mode of prediction, what we would use for further computation and evaluation of the algorithm, will be basically an average across the classes, average across the samples. So we'll get a tensor with the length of 5 for corresponding to each of the class, the probability of each of the class. And then the final class prediction will be argmax of this tensor. And the uncertainty can be quantified as an entropy of the prediction of the ensemble prediction. So the entropy computation is just right here in the code, and this would be an uncertainty value. Of course, the question is it a big uncertainty? Is it a small uncertainty? What does this number mean? And for this, a good idea is try to compare this uncertainty to the uncertainty of other testing examples to see where it stands in the distribution. And particularly what we could do, we could look at the correspondence of uncertainty and the type of the classification, either it's correct classification or incorrect classification. This is because usually uncertainty is evaluated by corresponding it to the error from the assumption that higher uncertainty values should correspond to an increased likelihood of erroneous predictions. So what we'll do, we'll build the distribution of our uncertainty, which is an entropy, for correctly classified and incorrectly classified examples. And what we see is when examples are incorrectly classified, the uncertainty, the median uncertainty is higher than for examples that are correctly classified, which can serve as some kind of sanity check for our uncertainty. In the end of this notebook, there are some limitations mentioned for the Monte-Carlo dropout method that we have partially discussed. First of all is the computational cost that increased with the number of samples that we want to generate. Second is the hyperparameter sensitivity that has been shown in several studies that concerns both the choice of the dropout scheme, where you place your dropout probability that you use in training and testing, as well as the number of samples that you generate. There are several other limitations, including the dependence on the architecture that you're using, the trade-off between uncertainty and accuracy, and the calibration of this uncertainty estimates. I'm also providing some frequently asked questions about the number of samples and dropout probability, and those are not strict rules. You can play with very different probabilities, but I would say it's more of a idea that you can get about the values when you try to choose something for your application. This said, you will always need to play with different parameters and evaluate the quality of your uncertainty estimates if possible. With this, we end the hands-on session. Please don't hesitate to ask us any questions, and I hope it was useful.